Speech recognition, or speech-to-text (STT), refers to technologies that enable the recognition and translation of spoken language into text by computers. We can say that the history of speech recognition technology dates back to the end of the 19th century. Then, Alexander Graham Bell developed the photophone, which allowed for the transmission of sound over a light beam, and Thomas Alva Edison developed the phonogram to record the sound. Of course, if you want to recognize speech, you first need to record it. In 1952, Bell Laboratories developed the first speech recognition device, known as the Audrey system, which was able to recognize digits spoken by a single speaker. In 1962, IBM demonstrated the shoebox, a machine that could recognize up to 16 spoken words. Early approaches in the 1970s and 1980s used dynamic time warping and hidden Markov models. In the 1990s, the first commercial speech recognition systems were released, allowing users to control their computers using voice commands. These systems relied on large databases of speech samples and statistical models to recognize speech accurately. In the 2000s, the development of machine learning and artificial intelligence technologies allowed for the development of more sophisticated speech recognition systems that could recognize speech in a more natural way. In 2002, Microsoft integrated speech recognition into MS Office products. The first mobile phone to use decent speech recognition technology was the iPhone in 2008. Let's see how it works. As seen from the historical overview, the simple tasks in speech recognition were solved relatively fast. Of course, this was based on the small vocabulary size. If you have only two words, yes or no, this can be solved accurately. Similarly, for digit recognition, 0 to 9 and O, this is still a very easy task. But it gets much more difficult when dealing with the vocabulary that humans use, which can make up to 60,000 words or even more. Now we sketch how a speech recognition algorithm works. We start with a waveform of a sound recording. The next step is sampling. Most information in human speech is in frequencies below the Nyquist frequency 10 kHz, so 20 kHz would be needed to capture all information. However, if we are sending the voice through a microphone in a phone or similar, the sampling rate is already lower, such as 8 kHz for telephone conversation. The following step is windowing. The recording is cut into short segments, as shown in the example. What we show here is a sliding window, meaning that there is an overlap between the two consecutive windows. The speech extracted from each window is called a frame. The windowing is characterized by three parameters: the window size or frame size in milliseconds, the frame stride, also called the offset, and the shape of the window. In the following step, we calculate acoustic features from the windows. This is done using large audio feature libraries. Important component in these features is the Fourier transform, which transforms time domain recordings into spectra. In computing, the discrete Fourier transform is used. Among the audio features, male frequency capstrom coefficients, or MFCCs, are very common. These features make use of the Fourier transform of the recording and look at the power of the spectrum in different log-spaced frequency bands. This approach much more closely resembles human hearing than if we space them linearly. From this step on, speech recognition typically uses neural networks to get the connection between the audio recording and the actual words. An example of standard architecture is called Attention-Based Encoder-Decoder, or AED. Speech recognition technologies are widely used today. They are often coupled with the text-to-speech systems that we discuss in another video. You may find these technologies in personal assistant devices such as Amazon's Alexa, Apple's Siri, and Google Home to allow users to control their devices and access information using natural language. STTs also help people with disabilities. They are used in applications such as the automated consumer service, though I actually prefer talking to an actual human. In medicine, These technologies help medical doctors to make notes in a faster way than writing them down. They are also used in robotics to allow robots to interact with humans using natural language. At the end of the unit, you will find several questions to test your knowledge. Here is one of the questions. Which approach is typically used in speech recognition? Encoder-decoder neural network, Monte Carlo tree search, decision tree, or exhaustive search? What do you think?